This recording is for Friday, the 13th of April, Class 38. A couple of announcements before we get into the material. First of all, remember that the big final class project, that's due on Monday. So next Monday by 12 p.m. you need to upload your report and also the Excel file where you're doing your calculations. Upload it all to MU Online before class on Monday. Also, homework number 14, which is related to the cost estimation ideas we've been covering in the past few lectures, that will be due on Wednesday of next week, on the 18th, and you need to upload the assignment prior to class on Wednesday. Today's video is going to be covering two additional methods for us to extrapolate and project what costs of a project may be. In section 15.4 of the book, it talks about these cost capacity equations. And then also we're going to learn a technique called the factor method.
Now, here is a picture of a wastewater treatment plant. And when you fly any place on an airplane, if you look down and you notice big circular tanks like this, and there's lots of them, they're probably not swimming pools. All right? And it's interesting. Any city you fly into, if you look for it, you'll see these, because every city has to treat their wastewater before it's discharged into a lake or a river. So these are clarifiers. The circular ones are clarifiers, which is meant to allow solids to settle to the bottom of the treatment plant. And then these basins are aeration basins, which is where they're trying to force feed oxygen to microbacteria that will break down pollutants. So this is a wastewater treatment plant, and this is a pretty big one. You can tell that there are several different clarifiers here, and so I'm just estimating here, but this looks like the treatment plant that you'd need for maybe around 500,000 people, approximately. Now, here's a much smaller treatment plant. They've only got 4 clarifiers in this treatment plant. So the first thing we're going to look at today with cost-capacity relationships is, let's say that you had really detailed financial data for how much it costs to construct this bigger treatment plant. Maybe it would be possible, if you had another project down the line, to estimate in advance what the costs are going to be for the smaller wastewater treatment plant based on what you know for the larger one. Now, what could be a challenge as far as that goes? We've talked about bulk discounts in the past, and so how might that same idea apply here? What's a bulk discount? So if you buy a lot of something, you can often negotiate a discount with the supplier. So a facility that's this big may have some construction efficiencies and some material cost efficiencies that a smaller project like this couldn't capture. And so we may not be able to just scale linearly from a large facility to a small facility. So this larger one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 clarifiers that we can see. There's probably one here too. So let's say 18 clarifiers. So this has only 4. Most likely the price is not going to be 4/18ths of the bigger one. There's going to be some sort of a nonlinearity that we have to keep track of. The cost capacity equation allows us to do that. The first part of it, before we look at the exponent, if we ignore the exponent, it's pretty straightforward. It's saying, let's say that you know the price of a big thing. Let's say C1 is the cost of that big treatment plant. We knew that it costs $20 million to build that facility. So that is C1. And Q is some measure of size. It could be the flow rate of water that treatment plant is treating. It could be the number of people that it accepts wastewater from. So let's say my estimate was 500,000 people. So Q1 would be 500,000 people. C1 is $20 million. So in a case like that, what if we wanted to estimate the cost for a treatment plant that's only going to serve 100,000 people? So it would be 1/5 of the $20 million. So that's the linear approach. But what this is saying is there could be some correlating exponent that has to do with the fact that not everything scales linearly. So let's look at what these x values could be. If x is 1, then that's assuming that there is a linear relationship, meaning you get no discount for a big facility compared to a small facility. It's all the same, the scaling. If x is less than 1, that's an indication of an economy of scale, meaning that there's a cost advantage for a larger size. In other words, the cost advantage for a larger size means that the more you buy of something, you're actually getting a discount per unit of that item that's being purchased. But occasionally there are diseconomies of scale, meaning that the larger something gets, the more expensive it is to either build or to buy. And that might be because it's just getting so complicated that now new challenges are arising that wouldn't necessarily exist for the smaller version of the thing. It could be, in the case of water treatment, for example, bigger facilities have more strict rules that they have to follow than smaller facilities. And so it could be that there is a diseconomy of scale, that you're actually better off having 2 small treatment plants than 1 large one, because you would fall under some sort of a regulatory threshold. So just as an illustration here, I'd like you to put the numbers into the equation and see if you get the answer that it's said here. So we're given that a certain water treatment plant costs $1.7 million. So let's say that C1 is $1.7 million, and the size of that treatment plant is 0.5 MGD. So Q1 is 0.5 million gallons per day. That would be the size of the treatment plant. Now, we have a correlating exponent x of 0.14, and we want to find out what's the cost of a 2 million gallon per day plant. And so, in this case, Q2 is 2.0 MGD, and so we want to know what is C2. Now, I've got it on the screen there that it's 2.06 million, but let's put it into the formula and see if that is the case. So we should have 1.7 million. The ratio of Q2 to Q1 is 2 million gallons per day to 0.5, and then you take it to the power of 0.14. What does that work out to? Can anyone confirm that it is 2.06 million? I see some nodding heads. All right. So let's talk more about the correlating exponent. Where does that sort of information come from? Well, tables like this. There are lots of different industries out there. Wastewater treatment is just one illustration that's provided by the text. There are different things that you need for a wastewater treatment plant. You may need to purchase a centrifuge for spinning things. Now, let's go back to the definition of correlating exponents here. If it's greater than 1, that means there's a diseconomy of scale, meaning actually you get penalized for buying more instead of getting the bulk discount. So most of these have the exponent less than 1, meaning that if you buy a bigger one, you're getting more value per unit purchased. But some of these, there is a diseconomy of scale. So an aerated lagoon has a X value of 1.13. An aerated lagoon, what that basically is for a really small town that maybe only has a few hundred residents, what they do, instead of putting together a fancy treatment plant with lots of pumps and moving parts that could break down, if it's a small town, sometimes what they'll do is they'll just take all of the sewage into a large pond and then just stir the pond and let it break down over the long term. And that's an example of an aerated lagoon. And what this is saying is, actually, the bigger the lagoon is, the more expensive it is. So that there's some sort of a disadvantage. It could be that real estate costs get too prohibitively expensive as you have a larger and larger area. It could be that if you've got a really large-sized lagoon, it's harder to put the mixing apparatus in the middle of a huge pond compared to a small one. So there's just something challenging about it getting bigger. And the same is true for sludge drying beds, which is another thing that's related to just spreading material out over a very large area. At the end of wastewater treatment, you have some solids that have to be disposed of, and you need to dewater those solids, and one method is just to lay it out and let the sun sort of evaporate the water in the sludge. But a sludge drying bed has a correlating exponent of greater than 1, meaning that it actually is less economically viable the larger it gets. Okay, so to try these ideas out, I'm going to give you an in-class exercise that has, all right, it has a wastewater treatment plant that has 3 components, and you're going to need to estimate the cost of the treatment plant based on some given information about the size of it, and also given previous costs. And we're going to combine this with what we learned in class last time, which is cost indexes. Remember, when you get cost data in the past, you can use that previous cost data and project it towards today by using cost indexes. And so I've got the formula on the sheet here. Yeah. Okay, before you get started on the calculations, let's just sort of read through the problem statement together to make sure we're all on the same page. The first thing is that we are combining the cost capacity equations with the cost indices. And so that means that there's old pricing data. Back in 2010, that's our earlier year, we had the smaller treatment plant that had this sizing and component costs. And so these component costs are what you're going to use as the C values. And then the sizing, it may be horsepower that becomes a Q. It could be flow rate, size. And then we want to know, back then the construction cost index was 137, but when this is going to be built in 2017, we project that that same construction cost index will be 164, meaning that things in the future are going to be more expensive than they were many years ago in 2010. So not only is this facility going to be a different size, but also the time value of money and the effects of inflation are showing themselves. And so find the cost of each component using this formula and then add all of the component costs together. All right, let's talk about the different pieces of the cost estimation here. What we're saying is we're trying to find out how much this new aerated lagoon is going to cost to construct based on data we have from several years ago. The new one is bigger. So we have the original cost was $3.3 million, and there's a difference in size and a difference in time. So these two factors, the 3.13, that is the size factor that says how much more costly, how many times more costly it's going to be because of the increase in size. And then the 1.197 factor is the fact that prices have increased by about 20% in the intervening years. So 1.197 adjusts for the fact that construction costs will be elevated. So we do the same thing for the lagoon, the blower. Now the lagoon has a penalty for size increases. 1.13 means that the larger you get, the more increasingly costly it is, whereas the blower has a nice value that's below 1, so that you're getting far more than double the capacity at just barely double the price, in spite of the fact that there's the increase in cost due to time. So overall it should be $13.5 million approximately for the three components together. Any questions about cost capacity equations? They're very frequently combined with the cost indexes, because when you do a cost capacity equation, by definition, you're getting cost data for something that's already been completed, and you're planning for a project that's in the future. So it's inevitable that there's going to be a difference in cost because of just the change in time. The other thing we're going to talk about today is the factor method. And so the factor method is looking at how one component of a project sometimes can predict the overall cost of the project. So before I talk about this formula, let me just tell you about eating out in Dubai. Last year I was living in Dubai, and I love to go to restaurants, but sometimes you can get into trouble finding, it's a very, very expensive city. High-rise towers, the police are driving Lamborghinis, and all sorts of crazy excess. So as you'd expect, there's a lot of restaurants you go into and just, you're going to pay out the nose, several $100s per person. What I realized one time was that if I went into a restaurant and just looked at the price of a bottle of water, I could pretty much estimate what the whole meal was going to cost. And so if I went into a restaurant and a bottle of water was 3 dirhams, which is less than $1, then most likely my meal was going to be $10 approximately. I a couple of times realized, it was about a factor of 10 for, when I got the appetizer, the main dish, dessert, and the drink. A bottle of water was about a factor of 10 to the overall cost. One time, near the Burj Khalifa, which is that really tall building, I went into a restaurant, I sat down, and I noticed the bottle of water was 30 dirhams. So they wanted nearly $10 for a bottle of water. So I just sort of closed the menu, stood up, and made my way to the exit. Because I just wasn't in the mood, and also, I'm a cheapskate. So I didn't want to throw away $100 on a meal, especially because they were doing shisha in there, which is like the smoke that comes in with the long pipe, hubbly bubbly, sometimes it's called hookah. It just smelled like strawberry smoke in there. Plus, it was really expensive. So the idea there is that one component of a meal, the bottle of water, you can sometimes use that to factor up to what the overall project cost is going to be. So this formula is saying your total cost, including all of the components, is the cost of one piece of the project multiplied by some factor, h. So here's that illustration. My idea that a meal is 10 times the cost of water. So 3 dirhams for water, the meal is 30 dirhams. 20 dirhams for water, the meal maybe would be 200 dirhams. All right, so in the in-class exercise, we're going to actually take that idea and go one step further. Remember that we've talked about direct costs and indirect costs before. Well, when you are estimating the overall cost of a project, you have to take into account the fact that it's more than just the equipment that you purchase. In the case of the research project that I've told you about before, you know, a big part of that expense was the drilling of the wells, but then there was also the part that we had to give to Marshall to support the physical facilities, the utility costs, the human resources people who are managing the hiring on the project, and so on, the benefits. You know, there's a lot of indirect costs that have to be accounted for as well. So what this expanded formula is saying, if you know the cost of one piece of equipment, then you have to add up all of the factors for the direct costs. And so 1 plus the direct cost factors. And so then inside these brackets is going to be the overall direct costs of the project. But then you also have to account for the indirect costs that expand the amount that you're going to spend. And so now for the second part of our in-class exercise today, what I'd like you to do is consider the situation of a diesel generator that is costing $975,000. This says dirhams, but I mean dollars there. That says dollars on your paper. The cost factor for pouring the concrete pad is 0.39. That means that approximately the concrete pad accounts for 39% of the direct costs, and then the operator training is 16%. So if we go back to this formula from the previous slide, you're having to add together all of the cost factors, and you know 2 of the cost factors that will be incorporated into that. So 0.39, 0.16, you'll add it to this in the parentheses and multiply it by the cost of the major equipment. And the exercise here that we know is that it is $975,000 for the diesel generator. So there are other components there that we have to also account for, and then the indirect cost is 27% in this. So 0.27 is what you'll have to use for the other part of the equation. So the idea behind this example is that all you have to do is get a quote for one component of the overall system, and then just as a rule of thumb, whoever is doing this knows that usually that operator training is a certain amount of the money that's being spent, that the concrete pad the generator is sitting on is a certain fraction of the fixed component that we do have the cost data for. So that if you have done enough work in your field, you kind of have an idea of what these fractions are. Like when I had a new concrete driveway put in at my house, all the guy really had to do was look at the area. And he knew basically how much it was going to cost him in the form work, meaning the wood that goes on the outside of where the concrete's being poured. He had a basic idea of how much he's going to spend on the excavator, had an idea how much the aggregate's going to cost, just because if you know one component, then you can scale it up and predict the entire project based on that piece of data.